So last time we talked about arithmetic sequences, and today we are talking about geometric sequences. The difference between an arithmetic sequence and a geometric sequence is how we get from one term to the other. Arithmetic, we would add or subtract to get the next term. In a geometric, we multiply or divide the previous term to build a sequence. So this type of sequence is built by multiplying or dividing the previous term. So in this case, the ratio of any term to its preceding term is always constant, and this is called the common ratio. So if I had the sequence 2, 8, 32, 128, to figure out if it's geometric or not, I'm looking at what I multiply or divide one term by to get the next term. In this case, I am always multiplying by 4 to get the next term. Now we call the common ratio R, just like we called the common difference D in an arithmetic sequence. If it's not always apparent what the common ratio is, you can always take a term and divide it by its preceding term to get the common ratio. So in this case, 8 divided by 2 should be the same as 32 divided by 8, and 128 divided by 32. That will always give me what the common ratio is. So if you think about what this type of sequence looks like, if I start with some term A, then I multiply it by R to get the next term. My second term would be A times R. Then I multiply AR by R. I would get AR squared. Multiply that by R. I would get AR cubed. And that pattern would go on. If you notice, the fourth term has R cubed. So a similar idea happened in an arithmetic sequence. With adding, this happens with multiplication. So our explicit formula would be that the nth term is A, or my initial term, times R to the n minus 1. So in the 12th term, I'm going to take R and raise it to the 11th power. For the recursive definition, remember, two parts. The initial condition, so just tell me what the first term is, and then the formula part, all this is going to be, you take the previous term and multiply it by the common ratio R. So let's see how we can start using these formulas. In this first example, we just want to determine if this sequence is geometric or not. Remember that the common ratio has to hold true for any two terms next to each other. It can't just be the same for the first few and then drop off. So from 3 to 6, I multiply by 2, 6 to 12, 12 to 24, 24 to 48. I'm always multiplying by 2. So yes, this is geometric. My common ratio, R, is 2. So that means my explicit formula is A sub n equals my initial term, 3, times my common ratio, 2, raised to the n minus 1. All we did was take this general form of an explicit formula. We plugged in that A was 3, that's the first term, and R was 2. That was my common ratio. This form is then helpful to figure out, say, the 100th term or the 40th term. Now you'll notice in these geometric sequences, they get big pretty quickly, much quicker than an arithmetic sequence. For example, if we wanted to find the 10th term of this geometric sequence, we're going to use an explicit formula because that can help us figure out the 10th term without having to know the 9th, 8th, 7th, 6th, 5th, 4th, 3rd, 2nd, etc. So to find the 10th term, it's important it told us it was a geometric sequence, so we know that this common ratio, which looks like it's 3, is always going to be the same. So let's write down the explicit formula. The nth term is a, or the first term, times the common ratio, which we said was 3, raised to the n minus 1. So to find the 10th term, a sub 10, I'm just going to plug in 10 for n. So I end up with 4 times 3 to the 9th. 3 to the 9th is a big number. I can put this all into my calculator at once. If I do 4 times 3 raised to the 9th, I get 78,732. So you can see this 10th term got pretty big pretty quickly. The first 3 terms were 4, 12, and 36. By the 10th term, I'm already at 78,000. So compared to an arithmetic, it gets big very quickly. So similar to an arithmetic, we can also find the missing terms in a sequence, and we can do this 2 different ways. If we look at this sequence here, again, it's important it told us it was geometric. So from this first term 2 to the next term, I multiplied by r. From the second to the third, I multiplied by r. From the third to negative 54, I multiplied by r. Now just to get from 2 to negative 54, I could have multiplied by negative 27. So that means when I take 2, multiply it by r, by r, by r, I get negative 54, which has to be the same as multiplying it by negative 27. So this means that r cubed has to be negative 27. Well, if I take the cube root of both sides, r turns out to be a negative 3. So if r is negative 3, to get from one term to the next, I always just multiply by negative 3. So 2 times negative 3, negative 6. Negative 6 times negative 3 is a positive 18. Positive 18 times a negative 3 gives me negative 54, and it looks like that works. So negatives can come into play, and the order in the sequence can switch between negatives and positives if r is a negative number. In this next one, we're only missing one term in the geometric sequence. I only need one missing term, not 2. So from 48, I'm going to multiply by something to get the second term. From the second term to get 3, I multiply by r again. Now, if I were just to go from 48 to 3, I could have multiplied by 1/16. Notice how 3 got smaller. It's only a fraction of 48, so my r in this case is going to be a fraction. So 48 times r gives me 3. That's going to be the same thing as multiplying by 1/16. That means r squared is 1/16. Now this didn't come up in the last example when I had r cubed, because the cube root of something has to strictly be positive or strictly be negative. but when I take the square root of 1/16, I get that r could be 1/4, or it could be negative 1/4. The square root of 1/16 is also a negative 1/4. So I have two options of what the sequence could look like. If I have 48, some term, and then 3, and say my r is 1/4, well, 48 times 1/4 is 12. 12 times 1/4 is 3. That works. I also could have the sequence 48, negative 12, 3. From 48 to negative 12, I multiply by negative 1/4. And if I take negative 12 and multiply it by a negative 1/4, I will get a positive 3. So in this case, I have two different options of what that missing term could be. Both are valid, both make a valid geometric sequence. So just like we had an arithmetic mean to quickly figure out what that missing number is, we also have a geometric mean. The geometric mean of two positive numbers, say x and y, can just be found by taking the square root of x times y. So in this past example, I could have done the square root of 48 times 3, which is the square root of 48 times 3. That's the square root of 144, which gives me 12, and it could also be negative 12. So remember, the geometric mean gives you the positive, but it could be positive or negative. To see an application problem of this, let's consider a ball. So when a ball bounces, consecutive bounces form a geometric sequence. Again, it's important that it tells us it's going to be geometric. So think about this bouncing ball. On the first bounce, it's 100 centimeters high. We don't know what happens on the second bounce, but we know the third bounce is 49 centimeters, and then we want to figure out what the fourth bounce is going to be. This is going to keep going, getting smaller and smaller, but we want to figure out what these heights are. So if the first bounce is 100 centimeters, the third bounce is 49 centimeters. We want to find out what this missing second bounce is by figuring out, okay, what's the common ratio going on here? So because I am only missing one term in this sequence, I know the first bounce, the third bounce. The second bounce I can find by finding the geometric mean of 149. So if I take the square root of 100 times 49, by using this formula above, the square root of the two numbers, this gives me the square root of 4900, which is 70. So that means that this second bounce was 70 centimeters. Now to find all the consecutive bounces after this, I need to know what the common ratio is. So far, I haven't had to find that. But to find the common ratio, you just take any term and divide it by the term before it. So 70 to 100 should give me what the common ratio is. And if I wanted to check it, I could also do 49 over 70. And that also gives me this common ratio of 0.7. So if I know my common ratio is 0.7, to find this next bounce, I just multiply the previous bounce by 0.7. So if we want to write it as the fourth bounce is just the third bounce times r. We know the third bounce was 49. The ratio is 0.7. That gives us 34.3 centimeters for the fourth bounce. So in this case, we could use the geometric mean, but we also had to figure out what the common ratio was. So I'm going to tell you to pause the video here, try the next 5 problems printed in the guided notes as the checkpoint, and then I will go through the answers. So pause the video now. So let's see what the answers are. For number 1, it is geometric. The common ratio was always times 6. So yes, it is geometric. R is 6. For number 2, find the 8th term. You should use the explicit formula. And the 8th term comes out to be 640. For number 3, the explicit formula would be 625 times 0.2 to the n minus 1. When you write the first 5 terms, it's 625, 125, 25, 5, and 1. Moving on to the last 2, in this example with the radioactive substances, if you used geometric means, you would find out that this middle term was 928.15. The common ratio comes out to be about 0.51. Depending on how you rounded, you might have something slightly different. But if I'm always multiplying by 0.51, I would get that after 3 hours, it was 243.27. And after 4 hours, there was 124.01 grams left. Again, I found this initial 928.15 by taking the square root of 1806 times 477 to find out the geometric mean between these 2 values. So for number 5, you use geometric means twice. If you first find the geometric mean of 0.5 and 312.5, you would get 12.5. The geometric mean of these 2 is 2.5, and the geometric mean of these 2 is 62.5. So when there is ever an odd number of terms missing, you can use geometric means. You just might use them more than once.